Okay, let's look at current and resistance. We're going to talk about the flow of electricity, and so your book sort of introduces current here as a precursor to discussing the flow of electricity along the axon in your nerve cell. But also, you might encounter electricity later in whatever you might be doing, and we'll talk about current flow through the body as well. So current is the flow of charge. We're going to define it. We'll call current I. We're going to define it as charge over time. So in very much the same way that a speed is distance per time, a rate of changing your distance, this is the rate that charge flows past a point at a given time, or in a given time. So if I pick a point in space, and I count the number of charges in a given amount of time, and I divide those two values, that will be my charge. Often, the units of this are the amp, or the ampere. So you've probably seen amps on your electrical devices. They often have the current that they use on the back of the device. Sometimes we'll see this as amp. Sometimes we'll see it as a capital A. But the basic SI units of this are coulomb per second. Remember, coulomb is a charge, and per second is our time. So this is going to be charge per time, which gives us a coulomb per second. And 1 coulomb per second is equal to 1 amp. A resistor resists the flow of electricity. And you can think of a resistor as a pipe for the flow of electricity to go through. So we can think of it as a pipe, like water might flow through. Pipe has a couple dimensions that we can think about. It has the area, the cross-sectional area of the end, and then it also has the length. All right. Now let's do a similar thing like we did before with the capacitors. The resistor resists the flow of electricity. So if the resistance goes up, that means that it's going to resist the flow of electricity more. Okay? The measure of resistance is just like it sounds. How much does this device resist the flow of electricity? High resistance means it resists it a lot. Low resistance means it doesn't resist it that much at all. So if the area goes up, what happens to the resistance? Does the resistance go up? Does the resistance go down? Or does the resistance remain the same? So if the area of my resistor, or thinking of it as a pipe with water flowing through it, if the area of this gets bigger, what happens to my resistance? Does it go up? Does it go down? Or does it stay the same? Again, you can think of this also as like water flowing through a pipe. If I make my pipe bigger, will it be easier or harder for water to go through it? So if I make my resistor bigger, will the resistance increase? That is, it would be harder to flow. Will it decrease? It will be easier to flow, or will it remain the same? Doing really great on this. We'll just do a few more seconds. I'll stop at 45. Okay, awesome. B is right. If the area goes up, think of a pipe, right? It's a lot easier to push water through a big pipe than it is through a tiny little needle or whatever. All right? Now let's think about the other dimension, the length. Now, what if the length goes up? What will happen to the resistance? Will it be harder to push electricity through that device, easier, or will it still be the same? If I just make the resistor longer, or thinking also about the flow of water, if I make my pipe longer, keep the area the same, but just make it longer. Let me give you a hint. It's not C, that the resistance will change, okay? So if I make, it's not D either. If I make my pipe longer, it will change the resistance. Will the resistance go up or will it go down? My pipe if I'm thinking about water, or my resistor if I'm thinking about electricity. It's not C. I'll stop at 1 minute. Okay, good. A is right. If the length goes up, the resistance also goes up. Think of a hose and you're trying to push water through it. If I have a hose this length and I try to push water through it, that's fairly easy. But if I make that hose like a mile long, it's going to be a lot harder to push that water through that hose. And the same is true for resistors. If my length goes up, my resistance goes up. And so we get an expression. This is on your equation sheet. We get an expression a lot like what we got for capacitance. And that expression is that R is equal to rho L over A. I have a direct relationship with L. I have an indirect relationship or an inverse relationship with A. And this is something called the resistivity. The resistivity is dependent upon the material. If the resistivity goes up, that means I have a big resistance. If the resistivity goes down, that means I have a small resistance. Let me ask you a question. Which of these has the higher resistivity? Does wood or copper have the higher resistivity? Wood or copper have the higher resistivity? Which of these materials, wood or copper, has a bigger value for rho? This is just a constant. It's for particular materials. It describes the resistance of that particular material. If rho is big, the material is very resistant to the flow of electricity. If rho is small, it's not very resistant to the flow of electricity. I'll stop at 35. 35. Okay, awesome. A is right. Wood has a higher resistivity because it resists the flow of electricity. That's just a value. We determine it experimentally. Okay. Let's see. What kind of dinosaur has a very extensive vocabulary? Dinosaur. Okay. Now, there's a rule that relates current and resistance. This rule is called Ohm's law. It's a pretty basic of any electrician. If you've done any kind of electrical work at all, you've probably heard of Ohm's law. And it describes the relationship between the voltage, the current, and the resistance. It says that the voltage is equal to the current times the resistance. So for example, let's say that I have a circuit that looks like this. This is a resistor. This is a battery. And this circuit has current flowing through it. So this would be V. The current flowing through that circuit would be I, and the resistor would be R in this relationship. So if I increase V, and I keep R constant, if I increase the amount of energy per charge I give to my charges by the battery, what's going to happen to the current, up or down? If I increase the amount of energy per charge, that's voltage. If I increase the amount of energy per charge, what happens to the current, I? Does it go up or down? It goes up. If I give my charges more energy, they're going to go through this circuit faster, or more than will go through the circuit. If I increase the resistance, I'll cause the current to go down. Or if I decrease this, I cause the current to go down. So be able to, one, like if I just give you a simple circuit, say, for example, I gave you, I don't know, 12 volts here and 6 ohms here. That's the unit for current. Be able to calculate the current. The current here would be V over R, R12 over 6, which is equal to 2 amps. 12 volts over 6 ohms, or 2 amps. Be able to do just a simple calculation like that. Ohm's law is pretty basic. Anybody that uses electricity has probably seen Ohm's law. Y'all might have seen it in high school physical science. Okay? So just know that Ohm's law, it's on your equation sheet. Know how to do these simple calculations. And then also know Like if I increase a certain thing, say for example I increase V, then I increases. Or if I keep V constant and increase R, then I will decrease. Be able to interpret that equation in that way. If I change one of the variables, what happens to one of the other variables? All right. One other thing is the concept of power. We've seen power before. Power is equal to energy over time. We saw it when we had the energy chapter, work and energy. We measured in a watt. 1 watt is equal to, since it's energy over time, it's going to be 1 joule per second. You see power on all of your electrical devices. A light bulb, for example, is 100 watts or 60 watts, or if you have one of these new CFLs, it'll be 10 or 13 watts or whatever. So the power describes how much energy per time it takes on. What can you think of as the most power-consuming device in your house? What do you think is one of the most power-consuming devices in your house? Which device in your house do you think uses the most power? The what now? The microwave is actually not that much power. Oh, actually, no, I take that back. It depends. If you have one of those big microwaves, yeah, it can pull like 1,000 watts or so. The what now? AC does pull a lot of power. What? The light's not that much, actually. So, like, you compare your microwave, which is 1,000 watts, to your CFL light bulbs, those fluorescent light bulbs, they just pull like a 1%, 10 watts, maybe 13 watts. And then you add them all up, then you get maybe a couple hundred watts. Anything else? The dryer, right, the dryer. Anytime you have a heating element in something, hair dryer, clothing dryer, even worse, or if you have electric heat in your house, that takes a lot of energy. Because basically you're shoving as many electrons as you can through this wire, causing that wire to heat up, and then you transfer that heat to your clothes or your hair or whatever, your clothes, your hair. What was the other thing? Oh, your house, if you use it for. All right. What about y'all, man? I hate drying my hair in the morning. I'm just in there for like half an hour to dry my hair. Y'all too? Yeah, that's my wife. She gets dry her hair in the morning. Okay. But anyway, anytime you have a heating device, it takes up a lot of energy. Okay. So let's remember that heating devices use a lot of power. One of our other expressions, so we have Ohm's law, which is this. Another expression that if you're an electrician or you do any work with electricity, then you'll know this expression, which tells me the power as it relates to the voltage and to the current. So if I have something that has a lot of power, that means it's going to have a lot of current. So your electric dryer, your electric hair dryer, all those things are going to pull a lot of current. And in fact, if you go look at the electrical devices in your house, often they'll have the power rating, say 50 watts for your clock radio, and then they'll also have a current, say a half an amp for your clock radio. Okay, so that power and that current are closely related. In your house, everything has the same voltage. Do you know that some things in your house operate at a different voltage? Like most things in your house operate at what voltage? Y'all know? Anybody know? About 120 volts. So if you plug something into that wall, you'll get a voltage, an energy per charge, joules per coulomb, of 120 volts. Or sometimes you call it 110 volts. It sort of depends how you look at it. But there's something in your house that operates at a different voltage. What is that? It even has a different kind of plug on it. I know. Often plugs have 3 prongs, but this plug has 4 prongs. The dryer. What else? No, not the refrigerator. The fridge doesn't use that much energy, actually. The stove. The dryer and the stove, and then also if you have electric heat, but that's usually wired directly into your wall. But your dryer and your stove have a different kind of plug, That's because they have a different voltage. So a dryer, an electric dryer, for example, let's say most things operate at 120 volts. But your dryer and your electric heater and a couple other things operates at 240 volts. That's why it has that extra prong, so it can get that extra energy. So your dryer could operate at 120 volts. There's really nothing that keeps it from operating at 120 volts. But what would happen to the current if I use my dryer at 120 volts? My dryer, I want it to pull the same power because it needs that power in order to dry my clothes. It takes a lot of energy to dry your clothes. So what happens if I make my voltage go from 240 volts to 120 volts? If I decrease my voltage, what's going to happen to my current? It's going to increase, right. So the reason we have this 240 volts on our dryer is because it allows us to have a lower current. Okay? So the dryer, since it operates at 240 volts, it can use a lower current. That is, if V goes up, I goes down. If your voltage on your dryer goes up, then your current on your dryer will go down. And that makes it safer to use. You don't want a really high current flowing through your house. Okay, okay. Let's look at static electricity. I want to show you the generator that I brought. Actually, let's see, we have about 20 minutes left. Or 30 minutes, right? Yeah, that was a joke. I know, we have 20 minutes left. All right, so I'm going to show you this. This is called a Van de Graaff generator. A Van de Graaff generator looks like this. Looks like that. There's a belt that runs inside of it, like this, and this belt goes around and around. So it goes up and in this direction. It just loops around and around. It's kind of like a big conveyor belt, but on end. And then there are these brushes down in the bottom. Down at the bottom that this belt brushes up against, these little bristles that the belt will brush up against. And it's kind of like when you shuffle your feet like this, and then you go up and you touch somebody and it shocks them, and then you laugh and you're like, what are you doing? And so it's the same way. When this belt goes on these brushes down inside of the base, it will pick up electricity, electric charges. So we'll get electrons that'll go up on this belt, and it acts as sort of like a conveyor belt for charges. Those electrons, when they come up here, they'll go onto this metal sphere, and I get these electrons that spread around all on this metal sphere. All right, so turn it on. I want to show you a few things with it. Stuff that we've already talked about. All right, first of all, y'all see the belt in there? Move. See how the belt moves a little bit? See the belt moving? Yeah. I might have to lose them.